Thank you. My talk is piecewise smooth solutions of quasi-normal form in the simple critical case. We consider the equation 1, where C is a function of two variables of t and x. Function C is a piecewise smooth function of the variable x for each non-negative t. Gamma is a constant. MXC is integrable mean value. Equation 1 is considered with boundary condition 2. It means that solution of equation 1 must be to be periodic function of variable x. We need to find the piecewise smooth solution of this boundary value problem in the variable x and determine the.
But it can be discontinuous, continuous solution.
How?
Sorry, should it be continuous or it may be discontinuous?
Maybe discontinuous.
Don't assume that it's continuous.
So we need to find piecewise smooth solutions of this boundary value problem in the variable x and determine the conditions for their stability. In this boundary value problem, these solutions are step functions of the variable x. So this boundary value problem is the quasi-normal form of one system of spatially distributed differential equations in the case when the matrix of the linearized system has a simple zero eigenvalue. So first we need to define the stability of solutions. So let C of x is a function that on the internal from alpha g to alpha g plus 1 is equal to some constant rho g and equals to 0 in this point alpha g. And this function is a solution of our boundary value problem. Then we consider the set of initial conditions. In this set, we have the small functions h g of x. In this set, we have the same function that here. Small perturbation, small function means in this case that the maximum of sum of absolute value of this function less than some positive delta number. So then we can define the stability of solution. Solution C of x is called asymptotically stable if for each positive epsilon there exists positive delta, such that if the maximum of sum of functions Hg is less than delta, then limit of this absolute value is equal to 0. So now we consider the issue of equilibrium states of boundary value problem. Ferri's theorem, the boundary value problem 1, 2 has solution C equals to square root of 1 plus gamma and C equals to minus square root 1 plus gamma. And these solutions are stable if gamma greater than minus 2/3.
Can we see the equation again? How do you study this subject?
Now I can show you. So now let us prove this theorem.
So you start from fixed points.
Yes. Let C of Tx is a constant rho, substitute it into equation 1. So we have equation 3 that has three solutions, rho 0, rho 1, and rho 2.
What's happened to the integral? The integral is not there. Integral over C.
Integral of constant.
Integral of constant.
So now we consider the issue of stability of row 1 and row 2. Let xi of tx is a sum of row 1, 2 and small function eta. Substitute it into equation 1 and discard the terms where eta has power greater than 1 when we obtain the equation 4. So let eta is a sum of two functions where integral from 0 to p over variable x of eta 1, 0 is equal to 0. Then we obtain the system 5. The second equation of this system has integral, so we integrate the second equation from 0 to p. And now we obtain the system 6. This is two ordinary differential equation. So solution of second equation tend to 0 because if coefficient in right part is negative, and the solution of first equation tend to 0 if gamma greater than minus 2/3. So therefore, if gamma greater than minus 2/3, these solutions are stable. Now consider the issue of existence of step solutions of boundary value problem 1, 2. So let solution has the form 7, where row 1, row 2 alpha is some constants. And substitute it into equation 1, then on the interval from 0 to alpha we have this equation, and on the interval alpha to 1 we have this equation. So to solve the system of two equations, we need a real parameter c such that holds this equality. And then we have this equation. From it, we can express the alpha. So if we solve this equation and have two solutions of this equation, we can substitute it into it. So we can see the alpha. Later, I will show you the graphs of alpha of C. Now we consider the issue of stability of these step solutions. Let C Tx in this form, where eta 1, eta 2 is small function, substituting it into equation 1 and discard the nonlinear terms. So we obtain the system 9. And as in previous case, we let eta 1 and eta 2 will be as sum of two functions, where integral from 0 to alpha of eta 1, 0 equals to 0, and integral from alpha to p of eta 2, 0 equals to 0. Then we have the system 10 of 4 differential equations. And also, as in the previous case, the equations where we have integrals, we integrate. First, we integrate the third equation from 0 to alpha, and we have this equation. And next, we integrate the fourth integration from alpha to p. So we have the system of 4 differential equations. The first two equations are simple ordinary differential equation. Their solution tends to 0 if this and these coefficients are negative. third and fourth differential equations are the system of linear differential equations. So we can
You remove the integrals. Let me see this.
yes, yes.
Yeah. You just the integral is everywhere.
Yes, yes.
Throw it away.
Da, yes. So from this system, we obtain the conditions of stability of step solutions. So where? So if this solution, if these conditions are true, then solution is stable. So here you can see the graphs of alpha of C here. The orange points correspond to stable step solution. The blue points correspond to unstable solutions. Well, this is the case where C is negative. There are all points as orange here and here, and this is where C equals to 1.5. And here is the situation when gamma equals to 2. So we can see that there is an interval on where these step solutions are stable. And also we have the situation where solutions are not stable.
Do you know the name of this picture? It's a bifurcation, right?
Yes, yes.
There are two bifurcations there.
Yes, yes. Mm-hmm. So in this research, we have proved the existence of two equilibrium states and determined the conditions for fair stability. We proved that this boundary value problem has a one parameter family of solutions depending on the parameter alpha in the form of step functions, and determined the conditions of stability for this solution. Also, I want to say that we actually considered the situation when original system of differential equations has two imaginary eigenvalues, and we proved that in this case also have step functions, step solutions, but we don't know nothing about their stability yet. That's all.
Okay, very good. Well, can you show us the system again? Start.
Yeah.
Yes. This M of C is an integral, right, over C.
Yes.
I wonder what kind of physical system this would be.
Oh.
You're trying to find C. And at the same, okay, so you're trying to evaluate
this.
Okay. You're trying to solve for C, and at the same time, you pretend you know the integral of this function that you're looking for. Okay, so M of C is the integral of the function you are trying to solve all the time, right? Okay, mathematically, I think it is all right. To do, you have to take derivatives with the integral and so on. But can you think of any practical problem that might could be described by this equation?
This equation is the quasi-normal form of one specific system of ordinary differential equations. This system.
Quasi-normal.
Yes.
Of a system of equations or of one equation?
Of a system of equations.
This emerges as a normal form. And what is this system of equations good for?
I actually don't know because I have this problem I have from Kashenko Sergei Alexandrovich.
Yes, I understand, but in any case, you should also ask and say, not only thank you for the problem, but where does this problem come from? Somebody may ask me one day.
Okay, I will ask him.
Because it's an interesting problem, and one would like to know where does it come from.
Okay.
Okay, fine.
Is there any questions?
Okay. Very good.
Thank you.
Okay, let's thank the speaker. You're finished, right?
Yes.